Hello and welcome back. In this video, we will finish up Chapter 10 with Section 10.4 on multiple regression. So, regression is normally using one variable to predict another, and we've been looking at linear regression. So what happens if we have more than one variable that we want to use to predict another? So here, our variables are going to be x1, x2, all the way out through xk, and we want to use all of these different variables to predict what the value of y should be. Note that this is called, this is again linear regression, even though it's multiple regression. It's linear because we're just taking each variable times a number and adding them all up. So this will form a straight line. But now it's not just in a plane, but we can think it'll be in 3 dimensions, 4 dimensions, and so on. So it's a little bit harder to draw, but still possible. This section uses a couple of slightly different names. Rather than just calling variables dependent and independent, the dependent variable depends on the other ones. The independent variables we call the predictor variables. And why predictor? Well, we're going to use these variables to try to predict y, and y is going to be the response variable. After we use these, we want to get some information, and that information is what we will call the response. So we'll use predictor variables to predict the response. Just like before, we're going to use technology to compute these guys. This is not something that you'd ever really want to do by hand. It is possible, but very messy, so I'm not even going to really go through that. Like before, what we want is a way to say, is our regression line, is our regression equation very good? So the first way to do this is to use p-values, and it'll give us a sense of how accurate are our results, or can we trust our results? And having a low p-value is good. Having a high p-value is going to be bad. And essentially what this means is that if we have a low p-value, it means that we have enough data to say the chances of us happening to construct this regression equation by accident are really low, which means that probably our data was very good, and we got an accurate result. So having low p-values for regression equations is good. Having high p-values means that we could have just gotten everything by chance, and it doesn't really say very much. Having a high p-value is bad. So we want low p-values, and the other measure of goodness, and this is actually surprisingly a technical term, so goodness of fit. So the other measure of goodness is what's called R squared. R, like the linear correlation coefficient from last time. R squared is called the multiple coefficient of determination. And essentially, the way that you'd read this is that R squared will range between 1 and 0. At 1, this means that our regression line, our regression equation that's describing the data, is a perfect fit. We're not going to expect getting R squared of 1 very often. It could be very close to 1, and when it is 0 or close to 0, it means that the data just isn't linearly correlated. So having an R squared close to 0 is sort of the bad end of the spectrum, meaning that we shouldn't trust our regression equation. So the other thing that we'll do just after I introduce R squared is we're actually going to adjust R squared. And the reason that we do this, there's one problem with using R squared by itself without adjusting it. and that is simply using more variables to predict the response makes R² go up. So even if your line, your regression equation isn't very good, just adding more variables to it somehow makes R² go up. So that's not very useful, because simply throwing more variables into there doesn't make it a better line in any sense. So we adjust R² using this equation. Again, we'll use technology to compute our adjusted R². But essentially what this does is it takes into account, well, how big of a sample are we taking? The bigger the sample, the better the adjusted R² is at telling us useful information. And with K, the number of predictors is the number of independent variables. This means that simply throwing more variables into the equation isn't going to make it just seem better artificially. It'll take care of that problem. So ultimately, we just want our adjusted R². It's just slightly better at giving us information about the goodness of fit than the original R². So the guidelines for just determining what the best regression equation is, well, first of all, you'd want to use common sense. If you're trying to predict someone's height, the color of their shirt is not necessarily going to be very relevant. So using common sense, quite often there can be, we can begin to start throwing away a few of the variables, thinking, okay, this isn't going to be relevant, this isn't going to be relevant. We don't want to do that too much. We don't want to make too many assumptions, but common sense is good. Like I was mentioning before, having a low p-value is good, and having a high adjusted R². So the closer to 1 R² is, the better. The closer to 0 the p-value is, the better. And then this last one is one that the book really emphasizes, and that is simply using fewer variables. And where this really comes up is if you have a couple of variables that you're using to predict the value of something, and by using multiple variables, yeah, maybe we get a slightly lower p-value or a slightly higher adjusted R². But maybe these variables will depend on one another as well. So it could be that some of your variables are related to one another and are determined by one another. So it doesn't add any extra information to use more variables. So the moral of this last line is simply, if you can get away with using fewer variables and you still have a good regression equation, do it. It's not worth adding extra complication by just adding extra variables. So I want to go through a quick example here. So this is just a practice problem on in my math lab, and it gives us a table, and what it did is it did multiple regressions, as in multiple regressions, on data from some cars. And what they were doing is they were measuring the fuel consumption in the city, and they were trying to predict that using the weight of the car, the engine displacement, and the fuel efficiency on the highway, the miles per gallon on the highway. So of these, trying to predict the city engine efficiency, the miles per gallon, we're trying to use the weight, the engine displacement, and the highway gas mileage to predict that. So they do all of this work for us, and they come up with so let's say that we want to use all three variables to make this prediction. They come up with the regression equation. So it's just going to be some numbers. So this is what, 6.89 times, minus this number times the weight, minus this number times the engine displacement, plus this number times the highway fuel gas mileage. And for each one, it produces a p-value. So every one of these has a very low p-value, which is good. So even if you only use the weight of the car to try to predict the city gas mileage, we still have a low p-value. We have a low p-value in each one of these, which means that these regression equations are going to be fairly accurate. And then we have the adjusted r-squared here. So notice that some of these are going to be a lot closer to 1 than others. So for instance, using all 3 variables has an adjusted r-squared of 0.93, whereas using only the weight of the car and the engine displacement has an adjusted r-squared of 0.72. So this means using all 3 variables is better than using just weight and displacement to try to predict the city gas mileage. However, if you were to compare the weight, displacement, and using all 3 of the predictor variables to just using the weight and highway, so you're getting rid of the engine displacement, the adjusted r-squared actually goes up a little bit. So it's better to not use the engine displacement than it is to use it if you're using both the weight and the highway gas mileage. So then, okay, so the weight and highway displacement seems to be the best out of just using 2 of them. And then when we come down to this bottom one down here, we also see one that's really high, and that's just using the highway gas mileage. So when we compare the highway gas mileage to using both the weight and the highway gas mileage, the p-values are both the same, and the adjusted r-squared is also just about the same. The only difference here being 0.015. So since the adjusted r-squareds are nearly identical, using just the highway is going to be preferable because we want to use as few variables as possible. So we want to use just the highway gas mileage as the predictor variable, as opposed to using both the weight of the car and the highway gas mileage, simply because it's fewer variables and the adjusted r-squared is nearly the same. So if we can get away with using fewer variables and we don't have to sacrifice any accuracy, we do so. So this bottom line here, using just the highway gas mileage, is the best predictor of the city gas mileage. And this sort of makes sense if we take a step back and we think about, okay, the weight of the car, maybe that affects the gas mileage, but in the city, but if you know what the gas mileage is outside of the city, that seems like a pretty good predictor just intuitively, and it comes up right here. It has a fairly high adjusted r-squared as opposed to anything else, and we're using the fewest number of variables. And I'll go through how to actually calculate the p-values and adjusted r-squareds in the next video.